In this lecture, I am going to talk about RSA and digital signatures. So RSA algorithm got its name from the last names of its three inventors, Ron Rivest, Adi Shamir, and Leonard Edelman. RSA is a public key cryptosystem widely used for generating public and private keys, primarily used to create digital signature for authentication and non-repudiation. However, it can also be used for data confidentiality and symmetric key exchange. Since RSA is a public key cryptosystem, it is also based on a trapdoor one-way function, which leverages the time it takes for computers to factorize large numbers into prime numbers. So the idea is that it is easy for computers to multiply two large prime numbers to get n. So p and q here are prime numbers, which when we multiply, we get n. However, it is difficult to reverse n or factorize n into two prime numbers p and q. So going from this direction to this direction is supposed to be computationally hard. And as you can see in this graph right here, as the size of numbers increases, the time required to multiply stays relatively the same, as you can see here in red. However, as the size of number increases, the time required to factorize that number into large prime numbers increases exponentially. To understand the working of RSA algorithm, let's first go through the related mathematical concepts that it leverages. The first concept is the idea of prime and relatively prime. We know that a prime number is any positive number whose factors are only 1 and the prime number itself. For instance, we have 2, 3, 5, 7, and 11, all of which are prime numbers because the only factors or divisors they have is 1 and the prime number themselves. So for 2, it's 1 and 2, for 3, it's 1 and 3, for 5, it's 1 and 5, and so on. However, two integers are said to be relatively prime if their greatest common divisor is 1. Also, two numbers can be relatively prime to each other, even if both of them are not prime. For instance, 4 is not a prime number, however, it is relatively prime to 7. Since the greatest common factor amongst the factors of 4 and 7 is 1. So 4 has factors 1, 2, and 4, 7 has factors 1 and 7. The greatest common factor amongst these two is the number 1. So this means that they are relatively prime to each other. So pause here and find out if the following integers are relatively prime to each other. So the answer is yes for both of them. For the first one, the factors of 9 are 1, 3, and 9, and the factors of 19 are 1 and 19. So their greatest common factor is 1. For the second one, the factors of 8 are 1, 2, 4, and 8, and the factors of 13 are just 1 and 13. So again, the greatest common factor or the greatest common divisor is just 1. The next concept used in RSA is Euler's Totient function, also known as the phi function. So the Euler's Totient function computes the number of positive integers less than n that are relatively prime to n. For example, if we want to find the Euler's Totient of 35, we have to first find all the positive integers less than 35 that are relatively prime to 35. So all the way from 1 to 34. Here, the numbers in red are the ones that are relatively prime to 35. Now, if we count the numbers here in red, that's 24 numbers that are relatively prime to 35. This means Euler's Totient function or the phi function for 35 is 24. Now think about doing this for a very, very large number. It would be very, very time consuming to find all the numbers less than that number which are relatively prime to it. There is another approach to finding the Euler-Totient function, or the number of positive integers less than n that are relatively prime to n. This approach factorizes the number to break it down into two smaller numbers, then calculates the Euler-Totient function individually on these numbers, and then multiplying their results. This should give us the same answer as the previous manual approach. For example, to calculate the Euler-Totient function for 35, we can calculate the Euler-Totient function for 7 and 5, because 7 and 5 gives us 35. In other words, 35 can be broken down into a product of 7 and 5. So we individually calculate Euler-Totient function for 7 and Euler-Totient function for 5, and then we multiply these two. So the Euler-Totient function for 7, if you calculate it manually, it comes out to be 6. And the Euler-Totient function for 5, if you do it manually, because now it's a relatively smaller number, it comes out to be 4. So now we multiply the results of these two, which is 6 and 4, and that gives us 24. However, of course, it should be easy to factorize this large number into two smaller numbers. So this approach is easy to do for smaller numbers such as 35, but it will be difficult to do on larger numbers. One interesting fact about prime numbers is that their Euler-Totient function value comes out to be the prime number value minus 1. In other words, for any prime number, the number of positive integers less than the prime number that are relatively prime to it is the prime number minus 1, which can be generalized into this formula: phi of n is equal to n minus 1, which only applies to prime numbers. For instance, the Euler-Totient function or phi function for 2 is 2 minus 1, which is 1. For 3 is 3 minus 1, which is 2. For 5 is 5 minus 1, which is 4. For 7 is 7 minus 1, which is 6. Similarly, for 11, we have 11 minus 1 or 10, and so on. So pause here and find the Euler-Totient function of the following three numbers. You can use the calculator at this link right here to verify your answers. For larger numbers, you can break them down into a product of smaller numbers and then calculate their Euler-Totient functions individually and multiply the results. For instance, to calculate Euler-Totient function for 13, you just have to do 13 minus 1. Why? Because 13 is a prime number, so this value comes out to be 12. For finding the Euler-Totient function for 30, you can do Euler-Totient function of 10 and 3. So this means that you can do for 10 and then for 3 and then multiply the results of these two. Similarly, to calculate phi of 15, either you can use the manual approach or you can do phi of 3 into 5, or phi of 3 times phi of 5, and whatever comes out here, you can multiply these two. So of course, for phi of 3, you just need to do 3 minus 1 because it's a prime number, so this gives you 2. Phi of 10, again, we could break it down into phi of 2 into phi of 5, and 2 is a prime number, so we have phi of 2 as 1. 5 is a prime number, so we have phi of 5 as 4, and then we found phi of 3 is 2. So we could say that phi of 30 is equal to 8, right? So phi of 5, again, because phi is a prime number, is 4. So again, phi of 15 also comes out to be 8. Now that we have discussed the fundamental concepts used in RSA, let's look at its public and private key generation algorithm. The first step is to select two random numbers that are prime. So we select P and Q as our two prime numbers. However, these two numbers should not be equal. So that's one criteria that we have to keep in mind. And that has to do with reducing the prime factorization problem to a square root problem. So the next step is to multiply these two prime numbers to get n, which is also referred to as the modulus. And again, if our prime numbers p and q were equal, then this equation just becomes p into p, or it becomes p squared. So I could easily find the two prime numbers by taking an under root of this value. That is why we should not keep our two prime numbers equal. They should be different. So after we have found the modulus n, then we calculate the Euler-Totient function of n. Now note that since n is equal to p into q, we can say that the Euler's Totient function of n is equal to Euler's Totient function of p times Euler's Totient function of q. And since p and q are prime numbers, as we just saw, for prime numbers, the Euler's Totient function is just prime number minus 1. So we could write phi of p as p minus 1 and phi of q as q minus 1. Therefore, Euler's Totient function of n is just equal to p minus 1 into q minus 1. Next, we calculate the two exponents. We have a public exponent e and we have a private exponent d. E is part of the public key and d is part of the private key. Now, the public exponent e can be any integer that is greater than 1 and less than the phi of n or the Euler's Totient of n. And it should be relatively prime to phi of n, which means that the greatest common divisor between phi of n and the chosen exponent should be 1. For instance, if the phi of n was equal to 10, then we could choose e is equal to 3, because then 3 is greater than 1, it's less than 10, and if you notice, there are no common factors between 10 and 3. So for 3, we have 1 and 3. For 10, we have 1, 2, 5, and 10. So the only or the greatest common factor that 10 and 3 have is 1. So we could choose 3 as our public exponent. Then how do we calculate d? To calculate d, we plug in the public exponent and the Euler's Totient function of n into this formula, which is e raised to power phi of n minus 1 mod phi of n. And we will not go into detail on how to derive this formula. We will just refer to this formula to calculate the private exponent d. So then our public key consists of the public exponent e and the modulus n. So this pair actually makes up our public key. And then our private key is made up of two values, the private exponent d and the modulus n. So pause here and calculate the public and private keys using the following two prime numbers. So the first step is to find the modulus by multiplying p and q. So here we have 5 and 11. Multiplying them, we get 55. Then we find the phi of n or phi of 55 as p minus 1 into q minus 1. So we have 5 minus 1, which is 4, and 11 minus 1, which is 10. So our phi of n is 4 into 10, which is 40. Now, depending on what value we choose for e, we will end up with different public and private keys. So let's choose e is equal to 3, since 3 is relatively prime to phi of n, or 40. They only have 1 as the common divisor, or the greatest common divisor. Then we calculate the private exponent d as e raised to power phi of n minus 1 mod phi of n. So we have e is equal to 3 raised to power phi of n, which is 40, minus 1 mod 40, which gives us 27. This means our public key is 3, 55. So e is 3, n is 55. And then our private key is d and n. So we have 27, 55 as our private key. So today, the NIST's recommended size for RSA-based public and private keys is at least 2048 bits, which basically means that the modulus or n value should be 2048 bits. And since it is the result of the multiplication of prime numbers p and q, they should each be 1024 bits long. Also, 65537 is commonly used as a public exponent in RSA public key. This value is seen as a wise compromise since it is famously known to be prime. It is large enough to avoid the attacks that small exponents in RSA are vulnerable to, and it can be computed extremely quickly on computers. And here is a public key of a website which is taken from its digital certificate through the browser. And so you can see over here that we have 65537 as the public exponent in this public key, and we have a very large modulus or n value here shown in hexadecimal. So now let's look at the RSA public key of a website. So let's look at Twitter because it uses 2048 bits RSA keys. So to view the public key of Twitter, using Firefox, you have to click on this lock icon, then go to Connection Secure, then go to More Information, and then we want to look at the certificate. So we're going to click on View Certificate, which will display information inside twitter.com's digital certificate. So what we want to look at is this public key information section. So if you click over here on the modulus, it's going to show the full value of the modulus. So this is actually 2048 bits or 2048 bits, as you can see over here. And so it's represented as hexadecimal to save space because it's a very large value. So this is essentially our n value, the modulus, which is one part of the public key. The other part is this public exponent, which is again 65537. Okay, so this is a value that is relatively prime to phi of n, or phi of this number. So that's our public key for Twitter. You can generate your RSA key pair using OpenSSL, which comes pre-installed on Mac and Linux. Here are the commands for generating a 2048-bit key pair, as well as the commands to print out the keys in text format for readability. So this first command will let you generate your public and private key pair. It's going to store it in this file, and it's going to be a base 64 encoded file. So if you want to look at the generated public and private keys values, which means you want to look at the modulus, the private exponent, the public exponent, then you want to use a command like this to decode that file and display the values in the correct format. You can also export the public key part from the key pair in a separate file so that you can actually share your public key with everyone. And again, that is going to be a base 64 encoded file. So if you want to read the values that are stored in the public key file, then you can use this command to display the contents. Now let's look at how to perform encryption and decryption using RSA. To encrypt a message for confidentiality, we use the receiver's public key, which means that we need the public exponent E and modulus n in their public key. Also, we have to first convert the message into a decimal string so that we can perform exponentiation modulo a prime number, which can only be done on decimal numbers. Moreover, the decimal version of the message to be encrypted must be less than n. For instance, if we have a word hello to encrypt, we will take the ASCII value for each letter in the word, which is going to give us a decimal version of the letter, and encrypt the ASCII value individually using the formula message raised to power public exponent modulo n, which is our modulus. Similarly, to decrypt the ciphertext, we have to convert it to a decimal string, and now we need the receiver's private key to decrypt the message, which means that we need their private exponent and the modulus n. So we take the ciphertext and raise it to power private exponent mod n, which is our modulus, to get back the plain text. Let's look at an example. Let's say our message is the decimal number 88 and the receiver's public key is 7,187. So our modulus here is 187, which means that we can encrypt this message since it is less than 187. Now to encrypt, we will compute 88 raised to power public exponent 7 mod 187, which is n. So this will give us 11, which is our ciphertext. Now to decrypt this ciphertext, we will use receiver's private key. So let's say receiver's private key is 23,187. So what we'll do is we'll compute 11 raised to power private exponent, which is 23, mod n, which is 187. So this will give us 88, which is our plain text. For large base and exponents, you can use this power mod calculator that I've provided at this link, because sometimes the Google calculator does not work properly to compute exponentiation mod prime number. So pause here and find out the ciphertext given this message and the public key. Then check if the ciphertext decrypts back to the message using the corresponding private key. So here is the solution. Note that message is less than the modulus, so we can perform the encryption. Our message is 14 and our n is 33. Now to get ciphertext, we will compute message raised to power e mod n. So we have 14 raised to power 3 mod 33, which gives us 5. So our ciphertext is 5. To decrypt the ciphertext, which is 5, we are going to do ciphertext raised to power d mod n. So we have 5 raised to power 7 mod 33, which gives us back 14, which is our message. Now, RSA's security lies in how hard it is to guess the private key, since public key is already public and is known to the attacker as well. Now, numerous approaches have been used to find the private key. The simplest one is to do a brute force attack and try all possible private key combinations. This, of course, will take a long time. The other type of attacks are mathematical attacks, which are focused on finding the Euler's Totient function of n or phi of n so that the private exponent d can be calculated. There are two approaches for this. First one is trying to factor the modulus n into prime numbers p and q and finding phi of n or Euler's Totient function of n as p minus 1 into q minus 1 to then find d. And the second one is to try to find phi of n directly using the manual approach by finding all integers less than n that are relatively prime to n. And then once we have phi of n, we can compute d because we already know the public exponent e. There's also another category of attacks known as timing attacks, which are focused on finding the private key based on the statistical analysis of the running time of the decryption algorithm after trying it on several ciphertext values. So we have seen how to generate keys and achieve data confidentiality using RSA. But RSA can also be used to create digital signatures on data. A digital signature is a cryptographic value calculated on the data using a secret key that is only known to the signer. So this private key is unique to the signer. Now the receiver of the signature or any third party can verify this digital signature using the sender or the signer's public key, since it is public. Now note again that both the public and private keys belong to the same key pair, which is the signer or the sender's key pair. So a digital signature achieves message authentication and non-repudiation, but it also achieves data integrity, since the digital signature is calculated on the hash value of the message, and we use hash values to ensure integrity of data. The popular digital signature algorithms in use today are RSA, DSA, and elliptic curve-based digital signature algorithm. You can go to this link down here to check which of these algorithms are supported by the various versions of the TLS protocol on Windows. This figure shows how to calculate and verify RSA-based digital signatures. To calculate the digital signature, we first calculate the hash value on the message and then encrypt the hash value using the sender's private key. The resultant ciphertext is our digital signature, shown here in bright blue. We can append the digital signature to the message and then send them over to the receiver or whoever has to verify the digital signature. To verify the digital signature, the receiver detaches the digital signature from the message and decrypts it using the sender's public key. Note that the public and private key belongs to the same key pair, which is the sender's key pair. So after decryption of the digital signature, the receiver gets a hash value. The receiver then recalculates the hash value on the received message by passing it through the hash function, which was used by the sender. So the receiver then compares the hash value that they have calculated with the one that they got from decryption. If the two values match, this means the signature is verified. So OpenSSL provides support for the creation and verification of RSA-based digital signatures on text as well as files. This slide shows the commands needed to create RSA signature on a JPEG file, as well as how to verify that digital signature. Here, tux.sig represents the signature file created on tux.jpg file. And so this command over here shows how to verify the digital signature, which is stored in tux.sig file. So we have to provide as input also the original file, just tux.jpg because we have to recalculate the hash value on that file. And then this means that we also have to provide the hashing algorithm that has to be used, because just like we saw, we need to calculate the digital signature on a hash value of the input, which is a JPEG file in this case. And we have to provide the private key during digital signature creation, and we have to provide the public key during digital signature verification. And note that both of these belong to the same key pair, which is the sender's key pair. There is another digital signature algorithm which is used in the digital signature standard proposed by NIST. This figure shows how the digital signature creation and verification works in DSA. The main idea is the same, that the digital signature is calculated on a hash value of the message using the sender's private key and is verified using the sender's public key. The algorithm also uses shared public parameters used in signature creation and verification. These comprise of a prime number P, a prime number Q, and the number G, which is computed using these two prime numbers. There is also a per signature random number known as K, which is only used on the sender side. As we can see here, it's being given as an input to the signature creation algorithm. The digital signature created using this algorithm is comprised of two values, R and S. So on the receiver side or the verifier side, again, we recalculate hash of the message and pass it as input to the verification algorithm, along with the two components of the digital signature, which is the value R and S, as well as the sender's public key and the shared public parameters. The verification algorithm computes a value x1, which is then compared with the value R. If they both are similar, this means the signature is verified. So you can go through this link right here to learn more details about the computation of values R and S and their verification in digital signature algorithm. One other thing to note is that in digital signature algorithm, we create a separate public and private key. So if digital signature algorithm is to be used for signature creation and verification, then the entities need to generate a DSA-specific public and private key pair. OpenSSL supports the creation and verification of digital signature algorithm-based digital signatures on text and files. So this slide shows the commands needed to create DSA key pair to be used for DSA signature creation and verification, as well as the commands needed to create the digital signature and the commands needed to verify the digital signature. So where can we use digital signatures? Well, we can use it to verify the authenticity of downloaded files. You will notice that many websites provide their digital signature next to the software download file. They also provide a mechanism to get their public key so that you can verify the digital signatures. So here is an example of one such website that provides a GPG signature with its software file that you can download and verify the signature on. Digital signatures are also used to verify the authenticity of a website's digital certificate before using the public key from that certificate. This is automatically done in the TLS protocol when you visit an HTTPS-enabled website. And another popular application of a digital signature is to verify the authenticity of transactions in blockchain.